Okay, let's begin. Today I start with this chapter Kinematics. This is basically chapter 6 of my book. Just to recapitulate, after a long time we are meeting and I missed last two classes. First one was some misunderstanding because one team was there with you, I was not sure. The second one, of course, a link failure, and we are fortunate today that we are able to make it. By the way, this lecture 11 has been uploaded already along with figures of this chapter. Let's take a look of what we did in our last lecture, which was lecture 10. Basically, we did mathematical review of the things which I am using very regularly during my discussion. So, vectors were defined as a column vector. I defined the length of a vector, defined the unit vector, also two products for vectors which are dot product and the cross product, and corresponding physical interpretations. Then how to do the differentiations of vector. Correspondingly, if there is a dot product and cross product, we use the chain rules. Then I defined linear independence. Here I wanted to spend little bit more time to make it clear, because later on during dynamics I will use it, and this is used in many other situations. Let us spend a few minutes here. You see, formally this is defined as for a set of n independent vectors, alpha I a I equals to 1 to n summation is equal to 0 would mean alpha I equal to 0. Let me go to my handwritten stuff. Here I want to explain you in little more details. So, for the time being, let me look at I equal to 1 to 2. This is alpha 1 a1 vector plus alpha 2 a2 vector equal to 0 vector. For the time being, concentrate on scalar quantities. So, scalar a1 and a2. For vectors, a1 and a2 may have many components, but for the time being, let us say I talk about a scalar quantity, and the same kind of definition is used. When we say a1, a2 independent, it means what? It means I should be able to assign any value I like. So, suppose if I say a1 equal to 1, a2 equal to 2, this means I can put any value. Okay. So, suppose if I put a1 equal to 1, a2 equal to 2, so then I put alpha 1 plus 2 alpha 2 equal to 0. If I have to satisfy this from this expression, it is clear that this expression will never become 0 unless alpha 1 is equal to 0 and alpha 2 equal to 0. So, this is the meaning of independence. If a1 and a2 are independent and alpha 1 a1 plus alpha 2 a2 equal to 0, then alpha 1 has to be 0, alpha 2 has to be 0. So, this property we use in getting some other kind of equations, particularly in dynamics we will use it, we will see it later. So, now the similar situation is here. So, since A1, A2 are independent, that means alpha 1 equal to 0, alpha 2. Now, for example, if they are not independent, A1, A2 not independent, means what? If they are not independent, it means they are dependent, right? So, A1 is dependent on A2. So, then alpha 1 A1 is equal to minus alpha 2 A2. In that case, A1 is equal to minus alpha 2 alpha 1 is A2. So, this is then the situation. So, if they are dependent, then this relation is satisfied to make this condition 0. But if A1, A2 are independent, then to satisfy this one, this has to be true. So, that is the explanation I wanted to give you. If you have quick questions here for independence, I can wait for about 15 seconds. So, you can ask me within 15 seconds. Okay, if no question is raised about linear independence, then we move to our today's lecture. First part, we take a remaining portion of my mathematical fundamentals. Matrices was not covered in the last lecture. After that, I will move on to the kinematics, which is the chapter 6. In kinematics, we define two terms. One is called forward kinematics, another is called inverse kinematics. And we will try to look into some examples of forward kinematics with respect to some planar robots, and most likely in the following lecture we will go to special robots. So, since matrices were the part of last lecture, so I go to last lecture. You remember we define every vectors as a column vectors. So, then a matrix A, I can write it as a columns of several vectors A1, A2, so and so forth up to An. If one can also write A as another matrix. So, if let me go to the paper here. Let us say I have matrix A, which is A11, A21 up to AM1, A12, then A22 up to AM2, and this way I go A1n, A2n and AMN. So, this is m by n matrix. Okay. So, now if I say this is my one column, this is my another column, this is my another column, I write it as a A1 vector. So, this is equivalent to this is A2 vector, and I define this as a AN vector. So, this can be written as A1 vector, A2 vector and AN vector. Now, the same matrix, if I define this, so these elements, So, if I define A1 as A11, A12 and then up to A1n, then if I define A2 is equal to A21, A2n, and then I define AM vector as AM1, AM2, this is A22 and AMN. That means I have talked about these elements defined as this one and these elements have defined as this one. Notice, as we wanted at the beginning of vector definition, every array of numbers considered as a vector will define as a column vector, as I have defined here. Now, I want to rewrite A in terms of these column vectors. So, then I should write A1 transpose. So, if A1 transpose happens, then what? Then this one gets transposed A11, A12, A1n, then A2 transpose. So, this will come A21, A22, then A2n, then the last one will be transposed here. So, AM transpose. So, this will be AM1, AM2 and this way AMN. So, a matrix, if I define its column elements as vector A1, these column elements as vector A2, then this is my matrix A. If I define these columns as vector A1, these elements as vector A2, then I will write matrix A as this way. So, the same matrix, the array of numbers, if you consider differently, then the way you write it should look different, but final result is same. Go to the presentation. So, that was M by N matrix. M by N generally is a rectangular matrix. It could be M bigger than N or M less than N. But if I want to define determinant of a matrix, I define it as a square matrix, because determinant of a matrix is defined only for a square matrix, as I have written it here. Determinant of A represented by this symbol like a mod A, and these elements are here. As per definitions, this is summation over minus 1 to the power I plus j A I j, determinant of they call adjoints A I j. If you are not very clear what are they, you can go back to your undergraduate mathematics book. They will define the adjoint, meaning of adjoint. We need not worry much. Most of the cases, if I do 3 by 3, I have given a definition for 3 by 3, that A1, for A1 adjoint is this one. That means, if you leave aside 1 minute. So, if I am looking for adjoint of A, so you remove these two row and column. So, whatever is remaining here is the adjoint of A here, and determinant of this is actually we are talking about here. Next is this is a summation. This is a summation here. So, we have to do summation. So, then the next A1 2 and then A1 3 so and so forth, and for which there is a simple formula that if you count A1, then we multiply A2 2 3 3 minus A3 2 2 3, then I take this element A12 here, then I go in the reverse side, that this into this, and then this into this minus this into this. You know what I mean. So, I am not spending much time here. So, this is the way 3 by 3 will be defined. For complex problem, there are algorithms. If you are writing your own program, you can write it. If you are using programs like MATLAB, just you put it A, it will give the results. Another important parameters which we need is the inverse of a matrix. A inverse, again inverse is defined for a square matrix only. So, do not expect that a rectangular matrix m by n will have an inverse. We have a definition called generalized inverse for square non-square matrix, but for the time being let us concentrate on a square matrix. So, A inverse is defined as 1 over determinant of A and adjoint of A. This is required to solve equation of linear equations, say A x equal to b. Let us come to the paper here. Suppose if I have A11, A12, A13, A21, A22, A23, A31, A32, A33 is equal to x1, x2, x3 is equal to B1, B2, B3. So, here I have written a 3 linear algebraic equations in 3 unknowns. Means I give you this value, 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 I give you this. So, that way I provide you all and I ask you what is this, what is this and what is this. In a matrix vector form, we will write this as a Ax vector is equal to b. In this I have given you A, I have given you B. So, x can be calculated as A inverse B. So, if you use the definition of A inverse, just explain, if you multiply it with B, you get the solutions. However, for real computational purposes, we do not calculate A inverse the way I have explained. That is one definition to calculate A inverse and finding out x. In practice, we do not calculate A inverse multiply with B to calculate x, rather we do the following. We write the whole matrix A11, A12, A13, A33. We apply what is known as Gaussian elimination. Again, you may refer to your undergraduate textbook, and then we bring it to a form where these things are zeros. So, this becomes a upper triangular matrix, and then we solve from there. I am not going to the details again. This is just the method you can find out in any linear algebra book, any linear algebra or matrix computation. So, the information which I am providing here is A inverse is defined in a way as in the transparency. I go back to the transparency. So, Generally, the above is not used. Solution of linear equations are used the way I have just explained in my handwriting. Another thing which we require in our matrix equations, which are used very frequently in robotics analysis, we will need it also, are the eigenvalues and eigenvectors. To find eigenvalues, the eigenvalues problems are defined as A x equal to S x. Let me try to write it here for you quickly. So, A x is equal to S, and here x is a vector quantity, here x is a vector quantity. So, A x equal to S x. So, if I put the vector symbol here, if I put the vector symbol here. So, this is actually typical eigenvalue problem, it is called A x equal to S x. This kind of problems appears in calculating the frequency of a vibrating systems and many other application. This is the most common application in mechanical engineering. Now, this equation, if you bring S x in the left hand side, so we will have A minus, so we will have A minus S and then identity matrix, and then we will have this x vector is equal to 0, this equal to 0. This actually implies that determinant of A minus S identity is 0, and so that is why I have written here determinant of S I minus A, you just change that sign here, should be equal to 0 in order to satisfy this equation. So, you calculate the what is S. Let me go to the paper to explain with a 2 by 2 matrix. Say, let us say I have a 1 1 minus a 1 2, a 2 1, a 2 2 minus S into identity 1 0 0 1, and the determinant is equal to 0, right. So, this will become A 1 1 minus S, this will be A 1 2, this will be A 2 1, and this will be A 2 2 minus S. So, this will lead to A 1 1 minus S into A 2 2 minus S minus A 2 1 A 1 2 equal to 0. So, this can be written as a square some coefficient here into a some coefficient equal to 0. So, an eigenvalue problem leads to a polynomial in S, and the root, if you solve solution of S in mechanical vibration problem, means natural frequency. So, this is just to give you a physical feeling that what is the utility of an eigenvalue problem. So, that is the reason I am giving you. If there is a 2 degree of freedom system, you want to find out its natural frequency, you will formulate it in the following manner. But in general, these solution of S are called the eigenvalues of this matrix A. Then if you want to find out the eigenvectors, then we put these values here and calculate S1 minus A x equal to 0, that was our original equation. Find x for solved S. These are called eigenvector. We will expand more whenever we need it, but this is one of the fundamental things it is good to know. So, if you have a time, please refer to your linear algebra book and revise it. Come back to the presentation again. So, with this the remaining portion of my mathematical fundamentals are done. Okay. So, if there are quick questions again here, I can wait about 15 seconds or 20 seconds if you have questions. So, you can ask me till I prepare to go to the figure of my kinematics. Okay, again no questions, we will wait until Friday. Now, I will ask face to face, right. Okay, now look at my hand before I show you the figures. With the help of my arm here, I will tell you a meaning of those two terms which are forward kinematics and the inverse kinematics. Suppose this is a robot, okay. I want to move from the position A where I am holding my fist, right. This is my fist here. From A, I want to move to point B, right. So, point A to point B. How do I move it? You see, I am moving this joint. Here I have a joint, here I have a joint, okay. So, I move from point A to B. If you ask me how to move it, I know I have a motor here, I have a motor here. So, to move my fist from A to B, I need to know how much I have to rotate this joint here and this joint here for my 2 degree of freedom robot here. This problem we call it inverse problem, okay. But I am sitting here, I have provided some motion and some motion, okay. Wherever it goes, I calculate and I say it has gone to point B. So, that is my forward kinematics. The meaning of forward and inverse are as follows. Here is my system, I have links, I have motors, and the motors are used to control my system. I just apply some voltage on my motors, motor starts move, motor starts move. So, it is my forward, straightforward application of torques providing some motions, and initially it is here I provided some voltage, the motor moves, my robot moved and I calculate where it moved. So, that is my forward problem. On the other hand, I am here and I would like to know how much these two move to from here to here. That is my reverse problem or the inverse problem, and that is required to control the robot, because we as a human being know very well where is A, that is in Cartesian coordinate, where is A. I know where is a Cartesian coordinate, where is B, but ultimately I achieve point A or point B by rotating these motors. So, I calculate this. So, that is my reverse problem. Now, you can look at my slide. So, this is the one I wanted to draw for you. So, I have here a 3 degree of freedom robot arm. I have a rotary joint theta 1 here, theta 2 here, theta 3 here. In this figure, they are not playing very important role, whether 3 or 4. I just wanted to explain the two concepts I have explained to you. So, here is the motor, motors are here, which provided some motions theta 1, theta 2, theta 3. So, theta 1, theta 2, theta 3 I have provided in the following manner: theta 1 as a function of some time, theta 2 as a function of some time, and theta 3 as a function of some time. So, I applied theta 1, theta 2, theta 3, which is shown by arrow in these directions. Because of those theta 1, theta 2, theta 3 motion, the end effector has moved in the following manner. So, end effector has moved in the following manner, which can be represented by position vector p and the rotation matrix q. So, this is the definition of a direct kinematics, providing the motion of joints, finding out the motion of the end effector. If you ask the reverse questions, that if I give you q and p, that means if I give you q and p, what will be the motion theta 1, theta 3. So, I calculate here in this box and here are my solutions. So, this is called inverse kinematics, or sometimes people call it as a reverse kinematics also. So, here in this example I am showing it. This is like a two link robot arm. So, I have link 1 and link 2. Link 1 has a length A1, link 2 has a length A2, and the position of this point in this coordinate frame is in the fixed coordinate frame is Px and Py. So, if I drop this line here on x, so this will be your Px, and if I drop this line on this, so this will be your Py. So, if I ask the question that if I have given theta 1 and theta 2 some values, what is Px, Py, that is my forward problem, and if I give you Px, Py, and if necessary phi, what will be theta 1, theta 2, that will be my inverse problem. Now, notice here, if I apply theta 1 here and theta 2 here, it will reach Px, Py. There is no other positions it can reach. But if I give this Px, Py, I get this theta 2, this theta 1. Also notice I can get, also I can get this is 1 theta 1, and if I draw a line here, and I can get this is another theta 2. So, notice for 1 Px and Py, I can get 2 theta 1 theta 2, but for given 1 theta 1 theta 2, I can get only 1 Px Py. What does it mean? For the direct problem means when I give theta 1 and theta 2, it has a unique solutions, that means Px and Py. But for inverse kinematics, where Px, Py is given, this has a multiple solutions. In this case, it has a 2 solutions, and inverse kinematics is required for the control purposes, because just now I told you for control purposes we are habituated in providing Cartesian coordinates. So, we will ask the robot to go Px, Py, and the controller will calculate what will be theta 1, theta 2. Of course, controller is programmed by robotists like me and you. So, then you have to decide in the program which theta 1, theta 2 you would ask robot to go, this theta 1, theta 2 combination or this theta 1, theta 2 combination. So, that leads to a set of another research domain. We are not discussing that part immediately. I just wanted to focus that an inverse kinematics has multiple solution and forward kinematics has unique solutions. So, here I am writing it, forward kinematics admits unique solution, and it requires simple multiplication and additions, whereas inverse kinematics admits many solutions, and as we will see soon through examples, it requires solutions of nonlinear algebraic equations, because there will be equation in terms of sin theta, cos theta, and we have to solve thetas where it appears with sin thetas and cos thetas. Okay, so how do we do it? So, let us discuss the simpler problem as far the subject is concerned, we have understood now forward kinematics should be a simpler problem, because it requires simple multiplication and additions. It has a unique solutions. So, let us discuss forward kinematics. First, we will discuss inverse kinematics later. So, forward kinematics, we go back to our homogeneous transformations representations. You remember this lecture here, that was I think couple of lectures before. We said if I have a point P and if I have a frame here, I can write the position of that point, and in the reference frame, in the fixed reference frame, using a homogeneous transformation matrix T, a 4 by 4. What does T does? T, if I go back, so T represents this point P and this orientation of this coordinate here in the fixed frame. So, in robots we have several such frames. So, okay, we go back. So, that was the general expression of T, but later on we have seen that if we use DH parameters, then between two coordinate frame, T represents this matrix. And to remind you, whenever you see this matrix, best thing is to partition first like this. Okay. So, here this portion represents the orientation of frame I plus 1 in frame I, and this will represent the origin of frame I plus 1 from the origin of frame I. So, these are the two definitions we will require for our forward kinematics. So, if T1 represents coordinate frame 2 orientation and position with respect to 1, if T2 represent the orientation and position of frame 3 with respect to 2, and so on and so forth. So, the total orientation and position T can be calculated as T1, T2 and up to Tn. Alternatively, I can break. So, these are all 4 by 4 matrices. These 4 by 4 matrices can be broken down to two other equations, which will be 3 by 3 matrix equations and a 3-dimensional vector equation. Let me explain on the paper. So, what we are talking about is this one. So, T is equal to T1, T2 and up to Tn. Now, look at this diagram. So, I have a fixed frame and I am generally represented this as a joint. It could be revolute joint, prismatic joint. I have a body here, then I may have a body here. Notice I am drawing a general 6-dimensional frame, and maybe this is body, and here I have the end effector. Okay. So, this is my body 1, this is my body 2, this is my body 3 and this is my body n. Now, as per our DH frame notations, this is my x1, y1 and z1. Of course, z1 would be the axis of rotation or axis of translation, depending on whether it is a revolute and prismatic. Arbitrarily assume this is z1. So, this is my frame 1. With body 1, I will have frame 2 as per our definition. So, frame 2 will be somewhere here. So, frame 1, so this is x2, y2, Z2, I will have something like here, and so forth. I will have the last one, maybe something here, where you can have x n plus 1, y n plus 1, z n plus 1. Okay. Now, what would T1 means? T1 would mean the relation between frame 1 and frame 2, this. So, this will be my T1, T2 will be this one. So, T1, if you look at T1, we will have a structure Q1 and then O2 in 1, this is 1 and this will be 0, 0, 0. So, Q1 will mean the orientation of this frame here in this frame. In other words, the columns of Q1 will be x2 representation in this frame, y2 representation in this frame and z2 representation in this frame, and O2 will represent this vector, the position of O2 in from O1. Similarly, T2 will give you orientation of this represented here, and it will have a vector quantity like this. So, so and so forth, if we come up to this, so you will get, so this is my final position P of the end effector. So, if you when you multiply this T1, T2, Tn, let us try to do for two such matrices, say T1 and T2. So, I have Q1, I have O2 in 1, this is 0, rather I have indicated as a phi, and then I have another one Q2, this is O3 into 1 phi. Phi means all zeros here, right. So, that means I am talking about these two bodies, right. So, these two bodies. So, now if you do the multiplication, so this will multiply with this. So, Q1, Q2, then this will go multiply with this. So, Q1 O3 into plus this will go with this. So, this with this. So, O2 in 1 and then this with this, which will be 0, and this with this will be 0. So, this is phi transpose, this and this 0, this and this 1. So, if you look at T1 into T2, this Q1 Q2 is nothing but rotation of the rotation matrices multiplication. So, this we have learned that Q1 and Q2, Q1 is the orientation of frame 2 with respect to frame 1, and Q2 is orientation of frame 3 with respect to frame 2. When we multiply, we will get orientation of frame 3 with respect to frame 1. So, this will be orientation of frame 3 with respect to frame 1. So, that we will talk about what is the orientation has happened, and this one if you look at what you are doing, this is my O2 frame 1, right. This is O2 in frame 1 from here to here. Then this portion is O3 in 2, that means O3 is represented in frame 2, but I am multiplying with the Q1, which means this portion means O3 in 1. So, O3 1 and O2 1. So, that means this vector I have represented here, this vector I have represented here, I can then add it up. So, this gives me this one. So, this component together O3, so this if I give a name O3 plus O2 in frame 1. So, in effect when I multiply T1 and T2, I can get the information of where is my this point for 2 link robot system. I can get from here where is the position of this point here and the orientation. So, these are the two things I require to know how to move a body from one frame to another frame. So, now notice here I have showed you in the transparency which will go back, I can either do T1, T2, but what are my results? Results are these and these. So, these operations I am doing it unnecessarily. So, if I do Q1, Q2, Q3, Qn, I will get this information. If I do O21 plus Q1, O32 and so on and so forth, if I do the calculations, I will get my position information. So, these are two alternative way. I can either do 4 by 4 matrix multiplications or I can do 3 by 3 matrix multiplications and this vector. So, they will both mean the same thing. Okay. So, let us go to the slide again. So, here you see that is the one I was trying to explain. You can do either T equal to T1, T2, Tn. These are all 4 by 4 operations, or you can do the operations here. In the bottom operations, if I do it, so unnecessary multiplication of zeros and ones which are happening in the above calculations will be saved. However, you have to treat them separately. So, if you want to write a computer program to do this thing, this may take little longer time for you to generate the codes, but the calculations will be very efficient. Here it will be very short time to write the code, but it may take little longer time in terms of CPU time, etc. So, now these theoretical concepts let us try to understand, starting from the simple example to complex examples. So, let us start with the simplest one, revolute, revolute. Go to the paper again. So, this is R R. So, I have one link here, another link there. So, this is my theta 1, this is my theta 2, this is my A1, A2. If you remember, we have done the DH parameters of this, and we have also calculated their transformation matrices. For the first problem, I am rewriting from the book, so which we have done in chapter 5. So, revolute, 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 revolute. So, we have revolute prismatic and DH parameter of a 3 link. Okay. So, we have this is your BI, this is your theta I, this is your AI, and this is your alpha I, and this was 0, theta 1, A1, 0, then this was 0. I am writing from the book. So, if you have the book, you can just look at this is in page 103, I am doing it, and then we have calculated its transformation matrix also. So, which appeared like T1 should be coming like cos theta 1 sin theta 1 0 0 minus sin theta 1 cos theta 1 0 0 0 0 1 0 A1 cos theta 1 A1 sin theta 1 0 1. Again I partition. T2 will be similar, except 1 will be replaced by 2's cos theta 2 0 0 0 0 1 0 A2 cos theta 2 A2 sin theta 2 0 1. So, these two transformation matrices I have just reproduced from the transformation matrices between the frames 1 and 2 and 2 and 3. So, just to indicate, this is my x1 y1, here I will have x2 y2, and here we will have x3 and y3. So, this will be my T1 information and this will be my T2 information. Okay. So, now let us multiply. So, if you multiply T1 and T2, so cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So, cos theta 1 cos theta 2 minus sin theta 1 sin theta 2, which is nothing but cos A plus B. So, I can write cos theta 1 plus theta 2. In fact, you can check similarly, this will be sin theta 1 plus theta 2, this will be 0, this will be 0, this will be minus sin theta 1 plus theta 2. You can please check later on, this will be this will be 0 0 0 0 1 0. Now, the last one. So, A2 cos theta 1 theta 2 minus A2 sin theta 1 theta 2, this is 0 and this is A1 cos theta 1. So, I will write A2 cos theta 1 plus theta 2 plus A1 cos theta 1. Okay. I will just shift it little left. Okay. If you look at the second term here, so this will be A2 sin theta 1 cos theta 2, this will be A2 cos theta 1 sin theta 2, which is nothing but sin A plus B formula. So, this will be A2 sin theta 1 plus theta 2, and then the last one will be A1 sin theta 1, this 0 1. So, this portion here, just hatching it, this will be the orientation matrix of the end effector with respect to frame 1, that means the reference frame. This one would mean position of the end effector with respect to the origin of fixed frame. If you are not convinced, let us apply our coordinate geometry knowledge and look it from our school level perspective and see what is these positions with respect to this one. Let us try to calculate. So, I look, this is a vector sum of up to this much and up to this much, that means this much. So, this plus this is the coordinate of this point along x1 and similarly along y. First, let us do. So, x, if you say this is Px, so this is Px. So, Px is equal to what? This component. So, this is A1 cos theta 1. So, A1 cos theta 1 plus this component. What is this component? So, this angle is theta 2, this angle is theta 1. So, this component will be A2 cos theta 1 plus theta 2, and you see this is the x component of this point, shown it by A1 cos theta 1. So, on my left hand A1 cos theta 1 and A2 cos theta 1 plus theta 2. You can try the second one, Py will be similarly A1 sin theta 1 plus A2 sin. And the last one, since it is a planar case, so there is no z component. So, Pz equal to 0. So, Pz equal to 0 also in this matrix. What about the orientation matrix now? Now, remember our direction cosine information. So, I am interested to relate this frame here, which is my frame 1 and frame 3. So, as per our direction cosine information, first column of my, that means here first column of my Q matrix is nothing but the projections of this one x 3 on x 1 and y 1. What is the projections of a unit vector which is x 3 on this? So, if this is my unit vector, what is its component along these directions? Since this angle I have just seen, this angle is this. So, here the angle is this angle, which is theta 1 plus theta 2. So, along this my projections will be cos theta 1 plus theta 2, and along y, that means this side it will be sin theta 1 plus theta 2. What is its component along z? What is its component along z? This is 0. So, this is 0. Now, if you want to write the second column here, so this will be the component of y 3, the unit vector along y 3 in x 1 x 2, and it can be very easily checked that this will come out to be minus sin theta 1 plus theta 2 cos theta 1 plus theta 2 and 0. And the last one, which is this z column vertically above the paper in the fixed frame, which is here, and these two are parallel. So, z 3 is parallel to z 1. So, obviously, it will have 0 0 1 structure. So, what I have shown you here is, I have shown you using a systematic approach of multiplying the transformation matrices between two links, here between link 1 and 2, or rather link 0 and 1 first. So, this is my link 0 and 1, and then 1 and 2, and then if I multiply those matrices, I get the relationship between the last one and the first one, which I have done it in this portion. And to show that this is done correctly, I have used my earlier knowledge of coordinate geometry and proven they are rightly done. So, whatever we are doing it here are right, and we can continue doing it for more complex systems. If there is a question, I will stop for another 15 or 20 seconds till I draw the diagram of my next example, which will be revolute prismatic. So, I will be quiet. If you have questions, ask me. Okay, seems things are going right. Today is very dark towards your side for some reason. I can only see black heads, only the hairs only, not the faces. So, B2 theta 1 0 0 0 pi by 2 0, and their transformation matrices, what they calculated, RPS they are calculated. So, T1 was calculated as, for the time being, to simplify my writing, cos theta 1 I am writing as C1 Sin theta 1 I have written as S1 minus cos 1. S1 means sin theta 1, minus C1 means minus cos theta 1, 0, 0. So, 0, 0, 0, 1. So, this I have taken from example 5.21. So, this is example 5.21. Then T2 is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, and this has 0, 0, B2. So, forward kinematics means I provide theta 1 and B2, because for this robot I have two variables, one is theta 1 and another is B2. Then for given these values, what should be my position and orientation of my end effector. So, Px, Py and what will be my end effector. Okay. So, we apply the way we have done our last problem. So, T is equal to T1 into T2. Now, multiply. So, cos 1 with 1, 0 with 0, S1 with 0, 0 with 0. So, what remains is only cos 1. Next one, S1 with 1, 0 with 0, minus cos 1 with 0, 0 with 0. So, this will remain as sin 1. Then this is 0 with 1, 0, 1 with 0, 0, 0 with 0, 0, 0 with 0, 0. So, all zeros. And the last one, from our experience, now we know it should be 0, because this is a homogeneous matrix. So, last row will always come out to be 0, 0, 0 and 1. We need not calculate. So, the next column now. So, next column C1 with 0, which is 0, 0 with 1, which is 0, sin 1 with 0, 0. So, 0 is all zeros. Sin 1 with 0, 0, 0 with 1, 0, minus cos 1 with 0, 0, 0 with 0, 0. So, all zeros. The third one, 0 with 0, 0, 1 with 1, 1, 0 with 0, 0, 0 with 0, 0. So, if you add, it will remain to be 1. Then the last one, cos 1 with 0, 0, 0 with 0, 0, sin 1 into 1 sin 1, 0 with 0. So, this will be sin 1. The next, sin 1 with 0, 0, 0 with 0, 0, minus cos 1 with 1 and 0 with 0. So, minus cos 1. So, 0 with 0, 0, 1 with 0, 0, 0 with 1, 0, 0. So, it is all 0. Last one, cos 1 with 0, 0, 0 with 0, 0, and this is B2 sin 1, and then last one is 0. So, this will be B2 sin 1. And similarly, the next one will be sin 1 with 0, 0 with 0. So, this is minus B2 cos 1, minus B2 cos 1, and the last one 0, 0, 0, 0. So, this is 0. So, now this is my final result. By the way, since this is an identity matrix, I should not have spent so much time multiplying with this matrix here. So, this should have been multiplied with this, and you see this is the same matrix actually here. Okay. Anyway, now I want to check, because this is a simple problem, I can check with my geometry whether my results are correct or wrong. This portion is my basically Q, and this Q means this is my x3, this is my actually prismatic joint directions. So, that was our Z2, and we have taken Z2 and Z3 parallel. So, Z3 and Z3 and probably Z2 and Z3. We might have taken I have to see the figure what we have taken. So, this was our Z3, this was our X3, okay, and X1, and this was our Y3. So, now this portion of the matrix Q is nothing but the projections of the unit vectors along the axis projected on frame 1. So, X3, the unit vector along X3 which is here has component along these directions, okay. And so, that will be just 1 minute, revolute prismatic X3, okay. So, these components if we try to calculate, then our theta 1 is shown to be as this one is a theta 1. So, the projections of a unit vector here along x1 and x2 y1 can be shown to be this one. I would request you to check, and if there is a problem we will verify when I am there. Let us look at the simpler one, this portion. This portion means Px, Py. So, what is Px? Px is, this is my B2 here, that means the variable prismatic joint length, right, and then this is my theta 1. So, actually this would turn out to be a B2 sin theta 1, and then it will be B minus B2 cos 1 and 0. So, this Q is the orientation of frame 3 in frame 1, and this portion would be P. So, P is position of origin of frame 3 from origin of frame 1. By the way, sometime you may get lost, why are we doing so many calculations? What is our purpose? Please do not forget your purpose. The purpose is, if I have a robot, if I am moving the robot using its joints by providing some angles, where is the robot going? I need to know, because later on I will have to control it, that if there is certain object which it should not hit, it should not go. So, I need to know for certain angular motion, certain translational motion, where is the end effector is going, and that process is the process which we are doing called forward kinematics. Okay, so, that was 2 link 1. Let me now show you for a 3 link planar. Again, till I draw the figure, you can think of a question if you have not understood so far. Okay, so now 3 link R, that means revolute, revolute, revolute. So far we are all talking about planar R, right. So, if you go back to our chapter 5, there we have checked T1, this portion is similar to 2 link, this will be cos 1 sin 1 0 0 minus sin 1 cos 1 0 0 0 0 1 0, and this will be A1 cos 1 A1 sin 1 0, see this is 1. Actually, if I just put 2 instead of 1, so this will become T2, and then T3, if you put 3 instead of 1, this will become T3, and going by the analogy of 2RR, or rather 2R, one can can show that this one will be cos 1 2 3 sin 1 2 3 0 0. Cos 1 2 3 means cos theta 1 plus theta 2 plus theta 3. Similarly, sin 1 2 3 means so this will be similarly sin 1 2 3 cos 1 2 3 0 0 0 0 1 0. Now, this portion will be like this. This will be A1 cos 1 plus A2 cos 1 2 plus A3 cos 1 2 3. You must be wondering how quickly I have written it. Actually, I have looked at this diagram. So, Px is nothing but summation of these lengths. So, this length is A1 cos theta 1. This length is A2 cos theta 1 plus theta 2, and similarly this length will be A3 cos 1 2 3. So, even though it is a minus direction, so this will be taken care of by the summation, because I am measuring the angle here. So, this is 1 2 3. So, theta 1 plus theta 2 plus theta 3. Okay. So, similarly I should be able to write A1 sin 1 blah 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 0 and 1. So, this is as simple as that. So, that was our planar. Now, I will go to the slide to break the monotony and also to show you some different example. So, we have been doing planar. Now, we will do planar and we will go little out of the plane. This robot you have seen long time ago, and this is called a Scara type of robot. Here I have at this junction, okay, I think it is not very, okay, at the right hand side, this is one joint here vertically, here I have another joint vertically, both are revolute. Here I have a revolute here plus a translatory. Let me see if I can find out a quick video for this thing, so that you will remember its motions. Okay, should be in our first lecture. So, here I think should be okay. Okay, so that was the robot, and now let me try to run it for you. Yeah. So, you see how it moves. So, this portion is the vertically going up and down, and this joint is moving here. It is now showing the prismatic motion. And as the jaws are moving about vertical axis, so that is the rotational axis. I will replay it again for you after this. So, I will replay it for you. So, you have just watch it. So, jaws motion are not counted in the degree of freedom of the robot, as I told you earlier. So, this robot has 4 degree of freedom. Okay, which are the 4 degrees of freedom? The 4 degrees of freedom are, so this is the vertical one here, 1, there is a 1 elbow here, that is the second one, at the wrist you have a third, so 3 revolute joint, and the fourth one is the prismatic one which was there. So, this is the prismatic one which is moving up and down. Okay. So, this rotation was due to the rotation at the wrist, the third revolute joint, okay, and this motion was due to the both first and second revolute joint rotation. Okay. So, now we go back to our presentation. So, okay. So, let us look at the architecture. By the way, if you have forgotten by this time, Scara means selective compliance assembly robot arm, selective compliance assembly robot arm, and this is used frequently in the assembly operations, particularly when the chips, the electronic chips in a computer board or a television control board or LCD projector or Xerox machine, to place those chips into the boards very fast accurately. Let us look at the architecture using which we can calculate the DH parameters. So, this was given as an exercise in my book at the end of chapter 5. So, this is the configurations, that is the first joint Z1 here, this is the second joint Z2, second joint means second revolute joint, first revolute joint, and the third revolute joint here, and then we have the fourth prismatic joint. So, it is DH parameters we must have calculated in that exercise, but here I will show you 1 minute. DH parameter 5, okay. Yeah. So, I will show you the results for the forward kinematics. Let us go to the paper again. So, this is now Scara. As I told you, the DH parameters were asked in the book as an exercise problem in figure 5.28, and based on those we calculate T1, which is cos 1 sin 1 0 0 minus sin 1 cos 1 0 0 0 0 1 0 A1 cos 1 A1 sin 1, this is B1 0. Okay. B1 here is a constant parameter, because the first revolute joint it has theta 1 as a variable joint. Then the second one is cos 2 sin 2 0 0 minus sin 2 cos 2 0 0 0 0 1 0 A2 cos 2 A2 sin 2, this will be B2 1. Okay. And then our T3, just to save some time in writing, this is 1 identity matrix 3 by 3, this will be 0 0 B3 1 0 0 0, and then T4 will be cos 4 sin 4 0 0 minus sin 4 cos 4 0 0 0 0 1 0 and then 0 0 B4 0. The way it has been written, the third joint is taken as prismatic one. Okay. So, which is not exactly the same as the robot I have shown you in simulation, but they can do the same task, because they have 4 degree of freedom, 3 rotation, T1, T2, T4 are the rotations, and then T3 is. So, we have the circle quantities are the variable quantities B3. Here we will have theta 1 of course as a variable quantity, theta 2 will have a variable quantity, and theta 4 will have. Now, if you multiply T1, T2, T3, T4 I will give you the final result. You please verify by doing the multiplications. So, this will be cos 1 to 4 sin 1 to 4 0 0 minus sin 1 to 4 cos 1 to 4 0 0 0 0 1 0. This will be a 1 cos 1 plus a 2 cos 1 2 a 1 sin 1 plus a 2 sin 1 2 b 1 plus b 2 plus b 3 plus b 4 1. So, 1 to 4 means cos 1 to 4 means cos of theta 1 plus theta 2 plus theta 4. Then sin 1 to 4 means sin theta 1 plus theta 2 plus theta 4. Here 1 2 means cos theta 1 plus theta 2. So, please verify whether this expression is correct by multiplying this on your own, and actually in my book there are several MATLAB programs, and one can just retype in a MATLAB environment and can get the results also. So, Scara is a robot which is like a planar except one axis, which is the prismatic axis coming down. So, I will just show you the next robot and request you to think on that, how to get the forward kinematics, but I will show you the result next time. So, this is what we call a articulated robot arm, where the first one is the vertical revolute joint here, and these are two parallel. So, this is figure 5.29 of my book. You have the book. I have given you the PDF of this chapter 5 also. So, please think, and let me stop here. If you have questions, we have 2-3 minutes to answer. If not, we will stop, but I will wait. Yes? Is there any question? No question? So, I am teaching very fine, am I? Yes, okay. Okay, so thank you. So, I have a class tomorrow and day after tomorrow also, which means if you can just browse through what I covered today, and probably the chapter 5, which was before mathematical formation, if you can just browse, have a glance to the notes or the book chapters, it will be even pleasant to understand tomorrow's lecture. Okay, thank you. Bye bye.